welcome to video notes 11, graphing the equation of the tangent line. So we were able to estimate what the equation line could look like on a graph, but now we'll have a more specific way of getting the actual slope from points for the tangent line at any point on the graph. And if you remember in class, I gave you all this equation and we took a little bit of notes on it, and I wanted to drive home the main point of showing you that, and that's so you could use it today. So as h gets really small, so this h, as h gets really small, because the limit as h approaches 0 is acting on h, so h is getting really small, the secant line that contains these 2 points, so those are the x values of the 2 points, remember? The secant line looks more like a tangent line because the 2 points get closer together. They're not socially distancing. So for 1 and 2, we are asked to sketch the graph of this function 6 minus x squared. So we start at 6 and then we go down from there. And you can use a calculator to do that if you're not very confident. We are not going to be quizzing over how well you draw quadratics in this. And we want to note the x-intercepts at radical 6 and negative radical 6, 0. And our y-intercept is at 0, 6. And if we're asked to find the slope of the tangent line at the given point 2, 2, then we need to use our equation. So this notation, f prime of x, that means m. That means the slope of the tangent line. So m means slope. So f prime of x is the slope of the tangent line. Another way you might see it is f prime of x equals m subscript tan to represent tangent. So if we're finding the slope of the tangent line, I'm going to reproduce my, we already did a, I'm going to reproduce my equation, which is called the difference quotient, by the way. So this thing that I'm writing out, it's a difference quotient because you're subtracting two y values over the difference between x values, which is h. I can't stress that enough, that this just means slope, this green that I've written. We're going to put our quadratic into this composition of functions. So this is where things get a little sketchy if you don't remember how to use composition of functions. So this says put f of x in the division expression and then replace the input with x plus h. So I'm going to take 6 minus, leave a blank, x plus h squared, because that's coming from my difference quotient. And then I'm subtracting the same function, but without a different and strange input, so it's just 6 minus x squared. And I need to subtract the entire thing, so I'm subtracting the entire 6 minus x squared. And then this will all be over h, with, of course, us evaluating as the limit as h approaches 0. So normally this would be really problematic because if we were to plug in, if we stopped here and we had everything in this limit and we looked at, well, there's an h in the denominator, and that's a problem because that makes our value undefined, well, we can manipulate the numerator so that this h divides away. So that's what we're going to do. So I'm going to I'm going to multiply out the binomial. So we've got x squared plus 2hx plus h squared minus 6 plus x squared, because I've distributed my negative. So this is some pretty solid algebra right here. I have kept my parentheses around my binomial because these are the same parentheses and they're needed for that negative that's out front. And then that's all over h. That hasn't changed. And then I'm going to distribute the negative, combine like terms. Hopefully my h can be divided out. So I've got 6 minus x squared plus, minus 2hx, because I'm distributing the negative, minus h squared minus 6 plus x squared. So if we look at this, we've got a couple terms that will cancel. The x squared terms, the 6 term, negative 6, and then what's left over is just this. So we're left with an equation, so negative 2hx minus h squared, that can be divided by h. Before, if we tried dividing the yellow terms that canceled by h, we could not get rid of them. So that means we also couldn't get rid of the h in the denominator. Now we can divide out the h in the denominator with the h's in the numerator. So that h divides out, one h from here divides away, and this h divides away. So we're left with the limit as x approaches 0 of negative 2x minus h. Now at this point, this is a really nice limit to evaluate because I can just plug in 0. I can evaluate the limit via direct evaluation. So our answer to the limit is negative 2x. Sorry, that h goes to 0. Negative 2x, which is fantastic. And if we are representing the slope of the tangent line, then we would say that the slope of the tangent line is negative 2x for this function. That means if we were to plug in 2, because remember we care about what's happening at 2, 2, then we could plug in 2 for x and figure out what the slope is. There's 2, 2. I put it in blue on the graph. So negative 2 times 2. I'm just putting my x value in that we're given equals 4. So, sorry, negative 4. So negative 4 is the slope of my tangent line that goes through 2, 2. And draw that nice line that goes through 2, 2 and has a slope of negative 4. So that means I can find whatever point, whatever slope I want because I have the generic equation of my slope. So this is the slope of my tangent line for the function. I can't emphasize that enough. You've found a generic way to represent slope on the function. This is revolutionary for a lot of reasons in the world of math, but it has a lot of engineering examples that go along with it. You can think of a lot of physics examples that go along with it. So we'll be looking at those as we progress. But we're kind of learning the basics of how slope even works in calculus, which is, funny enough, the same way it works in algebra. Now, that was B, so kind of a long question. The C is asking for, remember, we're not doing this. C is asking for, find the equation of the tangent line at the given point. Thankfully, we already have the slope. We could use point slope form to determine it, or you could just look off the graph, which is what I'm going to do. So y equals negative 4x and then plus 10. So we're going through 10. And then I've already sketched the tangent line, so there we have it. Alright, moving right along. This is asking for the tangent line, but without a graph and with all the fluff added to it. So I want to find the equation of the tangent line to this function. So I need to put 3x squared minus x cubed into the difference quotient. Which I need to write over again so we don't confuse it. So I'm writing, this says write my function, but with x plus h as the input. So I have to put x plus h wherever I see an x. Then minus my normal function, so 3x squared minus x cubed. Remembering to include parentheses because we're subtracting. And then all over h. Technically, we don't have to keep rewriting the limit because we're just going to use it at the end, so I'm not going to, for shorthand purposes, I'm not going to keep on rewriting that. So you might notice we have some things we need to write. Multiplying this out might just be kind of a grind for you, but that's alright, like we can do that. It's not a big deal. So I'm going to multiply this out real quick and be back with you. Ooh, finding slope is a crazy thing. We have to do a lot of multiplying. There's a lot of math involved and a lot of simplifying involved. So we have the same issue. We can't just plug in h, and we want to be able to. So if things follow the similar pattern, which they do here, then everything that does not have an h in it will cancel with another term in the numerator. So 3x squared, negative 3x squared, x cubed, negative x cubed. It looks like everything else has an h. So now I'll write the terms that have an h in it on this next line. And then divide that h in my denominator out of my numerator. So what's left over is 6x plus 3h minus 3xh minus 3x squared minus h squared. And then as h goes to 0, everything that has a 0 in it, or an h in it, will be 0. Lovely. So we get this nice 6x minus 3x squared answer. So this is the limit as h approaches 0. Yay. So that represents my slope. That's what we're finding. And we need that slope to find the equation of the tangent line. So we want to find the slope when x equals -2. And I know I've written a lot there on the right side, so we're going to come over to the left side, and I'm going to say the slope is equal to 6 times -2 minus 3 times -2 squared. So this is -12 minus 3 times 4. So it's -24. And then to wrap this up, I need a point from this equation. So the point that corresponds with -2 can just be found by evaluating the function. So I get +8 and 12, so 20. So the coordinate point at -2 is 20. And that's what I'll use in my equation of my line. And you'll have more space on your paper because we're not going to look at 4. This is a pretty long lesson as is. So if I use -220 in my point slope form, -24, then I'll plug all this in, and I'll end up with -24x minus 48 plus 20, so -28. Yay! So we found the equation of the tangent line algebraically. So that is the final answer there. Alright, so I'm sure we'll have to practice more of this in class. There's a lot of steps to a question like this. I'm going to break it up for you on your practice so that you kind of chunk them one step at a time. But you can see the 3 steps that we took. We found the slope, found the equation for slope, which is down here, and then we used that slope in our equation of the tangent line. But before we did that, we had to go through and find the coordinate pair, and that's the work that I did for the coordinate pair. And putting all those together, we were able to find our line. So it's a lot of work to find an instantaneous rate of change without a calculator, without other methods. We'll learn how to simplify this process considerably here in the future. So thanks for watching, and I'll talk to you later.